Okay, so welcome everyone to the weekly seminar. We're very happy to have Claudia Rodrigues with us today. She's an astronomer at the National Institute for Space Science or Space Research in Brazil. She got her PhD from the University of Sao Paulo with the main research topics on interacting binary systems and interstellar medium. And she is also very interested in optical polarimetry and specifically optical polarimetry instrumentation. And she's currently the coordinator for the development of the Spark 4 instrument. That's the simultaneous polarimeter and rapid camera in 4 bands. But she's also involved in other telescopes and other projects. And specifically, she's a member of the board of directors for the SOAR consortium and has served as the president of the program committee for the SOAR and the CFHT telescope. So today she's gonna talk to us about optical polarimetry of magnetic cataclysmic variables. Claudia, we're very happy to have you. Please take it away.
Okay, thank you. Thank you very much for the invitation and to have the time, to have the opportunity to talk about a little bit about our work here in Brazil in optical polarimetry, and specifically about magnetic cataclysmic variables. So let's start trying. Yes. To the next slide. So I think I have to introduce what is a cataclysmic variable. I have to be sure that everyone has this level of information. So this is a nice picture of a cataclysmic variable. What we see here is a binary system, a very compact binary system. This is very important. We are talking about a system which can be as small as the sun. Okay, in some cases, you see the two stars of this binary system inside the volume of the sun. So the star on the right is a main sequence or a slightly above the low mass star. So it's a normal star, it's a standard star. And on the right, just in the middle of this disk, we have a white dwarf. And because those stars are so near each other, are so close, we have the mass transfer from the secondary, from the main sequence star, that fills its Roche lobe. So we can have naturally a, 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 a flow of the mass from this star to the white dwarf, and in most cases, we have an accretion disk. What is important in those kind of systems is that most of the interesting phenomena that you see in this kind of system are not happening in the stars. What is interesting on those objects is in the mass transfer process. In most cases, this figure is a very nice picture, but it's not very, how to say, real, in sense that in the secondary star is not so bright, at least in visible and in high energy wavelengths. What we see is the accretion disk, is the mass that is being transferred from the secondary to the white dwarf. This is the usually this is the brightest component of the system. So what we see in cataclysmic variables is or are process occurring in the mass transfer phenomena. For instance, a nova object occurs in this kind of system. This is a thermonuclear brightening, or it's a brightening due to thermonuclear on the surface of the white dwarf. that occurs because of this accumulation of mass from this secondary to the white dwarf. But we are not talking about novas here. Another thing that I particularly think it's nice to remember is that the binaries are very common in the universe. So we probably have half of the stars on our sky, half of the stars are binaries. Depending on the mass of the star, this fraction can be higher. If you go to higher mass or to high mass stars, the fraction of binary system is very high. It can be one, near one. And so binary stars are common, and cataclysmic variables, they are a phase of the evolution of a binary system, a low mass binary system. And so they are not so, how to say, so weird. Cataclysmic variables are or is a phase that it can happen very commonly in the universe. So in this cartoon, to the right, you see the passes or the path of the evolution of high of systems in which you have high mass stars and they will become X-ray binaries. But we are interested here in the left panel, in which we have low mass stars evolving to become cataclysmic variables. I don't know if you see my mouse here. We have a cataclysmic variables, and before a cataclysmic variables, we have a very interesting process. For instance, the common envelope phase. I think there is a lot of physics that we do not understand about this phase. So the cataclysmic variables is a phase of very or a very not common, but it's very probable to have this kind of system in the universe. And from a cataclysmic variable, we can have, for instance, a supernova tipo 1A, or other thing is interesting. It's one way to have a supernova. It's not the only one. It's not the most important, but it's one of the possible paths to have a supernova. So this is the context of cataclysmic variable in stellar evolution contest. Okay. But here we are going to talk about cataclysmic variables in which the white dwarf has a large, huge magnetic field. So if we talk about a white dwarf that has a magnetic field on its surface of higher than 1 megagauss, what happens? What is the difference in the system? What we have is that this magnetic field, it disrupts the accretion disk. In this figure, we have a partial disruption, but this disruption can be complete. We can simply do not have an accretion disk, and the accretion flow, the flux of mass follows the magnetic lines. So we have an accretion process that is dominated, at least dynamically and near the white dwarf, by the magnetic field. So this is a cartoon in which we see on the top a standard magnetic CV. In the middle, we have magnetic CV in which the accretion disk is partially disrupted. So in this figure, you can see the magnetic lines and the mass going through the magnetic lines to the white dwarf surface. But you can also have situations in which you have only a magnetic accretion. You don't have an accretion disk. If the system, I have to say that the secondary, due to tide effects, is completely synchronized with the orbital period. So the secondary spin period is always the orbital period. But concerning the white dwarf, it does not always happen. So in the cases in which you have a complete synchronization also of the white dwarf, and this happens because of the white dwarf magnetic field, we have a magnetic cataclysmic variable that we call polar. And if you have a magnetic cataclysmic variable in which the white dwarf is not synchronized with the orbital period, we have an intermediate polar. And an intermediate polar, in an intermediate polar, we can have only a column fed. We can have or not an accretion disk. And this is important, and we have some results in this direction. Okay, so I like this slide because usually people when present the cataclysmic, the magnetic cataclysmic variables, they put the emphasis that what determine if we have an accretion disk, we have only a magnetic column, is only the magnetic field, but it is not completely correct. In fact, if we have or not a partial accretion disk depends on the magnetic field, of course, but also on the mass transfer rate. So we can, if we have a huge, a lot of mass going from the secondary to the white dwarf, we can have an accretion disk. Almost the truncation can occur only very near the white dwarf. So you can have a magnetic cataclysmic variable in which this, how to say this internal region is very small. So in order to really understand the geometry of an object, you need to have an idea of the magnetic field, but also on the mass accretion rate. And of course, a bit also about the white dwarf mass, but here the range is more limited. Okay, so if we think in from where we have the emission in a magnetic cataclysmic variable, the main the portion of this entire system that contributes most to observe the emission is a very thin region just on the surface of the white dwarf. For instance, if you go to the high energy, to X-rays, you don't see any star. You don't see the white dwarf. You don't see the secondary. You don't see accretion disk. You see only this tiny portion that you call post-shock region. Okay, so here on the bottom, we see the white dwarf photosphere, and you see the end of the magnetic accretion column, and from this region we have all the emission. We have cyclotron emission because we have a plasma, we have magnetic fields, we have the electrons making circular movements around the magnetic field. So we have cyclotron radiation. By the magnetic field, by the intensity of the magnetic field in those systems, usually the cyclotron radiation occurs in optical and in infrared regime. But we have also bremsstrahlung radiation. And this bremsstrahlung radiation occurs in X-rays. And by very simple energetic arguments, it's very easy to see why this happened, why the bremsstrahlung radiation occurs in X-rays. We are talking about a very, very hot region, okay? So in X-rays, so let's go to here. So in magnetic cataclysmic variables, we see most of the emission from the post-shock region. If you don't have an accretion disk, you can say that really what you see is only the post-shock region. If you have an accretion disk, a truncated accretion disk, as you have in intermediate polars, of course, we have also the disk in optical and the infrared. And usually the accretion disk is brighter than the post-shock region in optical and infrared regimes. So because of the geometry and the nature of those radiation, both radiations, bremsstrahlung and cyclotron, we can see a variability in those objects. Another important information about those systems is that because they are very compact, we are talking about binary system of, as I said, the size of the sun. The orbital period is about hours. So we can see the system in all orbital phases in a night. So you can see the system by different viewing angles during a night. And if we remember, the cyclotron radiation is very anisotropic. And more than that, it's polarized. So we can see the flux, the total flux, and the polarization of those systems varying very rapidly following the spin period of the white dwarf. If we think about a polar system in which we have the white dwarf spin, the secondary spin, the orbital period, they are all the same. So the orbital in this period is about few hours. So we can see the polarization varying, the flux varying in a scale of hours. And even in bremsstrahlung is a isotropic radiation. So if you see a optically thin region emitting bremsstrahlung, by itself, you cannot see variation in time, but you can have structures in the system. You can have the self-eclipse of the post-shock region. For instance, if you are looking for a white dwarf and during the spin of the spin of the white dwarf, in part of this spin period, the post-shock region is behind, is the occulted face of the white dwarf. You don't see the post-shock region, so you have a variation. And also because the absorption, because of the system can have a very complex geometry, the absorption, the matter that the system has between the post-shock region and the observer can vary along the rotation. And this can also produce a variation in the observed flux. So in X-rays, you can see variation only in flux because bremsstrahlung radiation is not polarized. But in optical, you can see flux and polarization varying, and from this we can get some information about the object. This is also a very simple idea, but I think it's key to understand some properties of those objects. Here on the left, we see a figure in which the circle is the white dwarf and the blue lines represent the magnetic accretion column. At some point in the Alfvén radius, the mass became dynamically trapped to the magnetic field lines. So the mass transfer follow the magnetic field lines. And here the green region is the pole shock region. Okay, so what we, and in the magnetic accretion column, we have, we can say that you have a free fall movement, a free fall condition. So we, in the pole shock region, what occurs a transfer or a change, a transformation of kinetic energy, this potential gravitational energy, it is transformed to thermal energy. And this energy can be very high. So we have a very hot pole shock region. So this was stated in this seminal work from Naizu. And doing very simple assumptions, we can have the temperature of this region by considering that the thermal energy in the pole shock region is the potential energy from the region in which we have the coupling of the mass flux to the magnetic field lines. And because of that, the bremsstrahlung radiation is a radiation that's basically defined by the temperature. So from this X-ray spectrum, you can have a direct measurement from the temperature in the region, in the pole shock region. This is not the complete story, because we know that the temperature is not constant along the pole shock region, and if to have the correct profile of temperature and density, we have to solve the shock that happens. So here, maybe here, on the top of the pole shock region, we have a shock front, and we have an advancement. We have an increase of the density between the front shock and the white dwarf surface. And in this region, the temperature and the density are not constant. And what we really observe depends in a very important way on those profiles. Okay? So this is the how to say, the context, the scenario of the problem that we try to understand. So if the title of the seminar is optical polarimetry, but I will start by talking about the model, because I think it's better to when you see the observations, we have already the model in our heads to understand how can we interpret them. So we have developed a code that's called Cyclops, because initially it had only the cyclotron emission of polars. Now we have also the bremsstrahlung. So in this code, we have the post-shock region represented by a 3D region, by a grid of points, and this grid of points follows a profile of density and temperature that are properly calculated by the shock solution. And also, so after filling this grid with the proper physical conditions, we do the radiative transfer to have the cyclotron emission integrated and the bremsstrahlung, they integrate the cyclotron and bremsstrahlung emission of this region. And our code also allows us for treat the self-eclipse of the post-shock region and even the absorption of the post-shock emission by the magnetic column that here we have the emission from the post-shock region, but if the observer is here, we have an absorption from the upper portion of the magnetic column, and we can treat it, we can calculate this with our code. And here is I think what is important to say here is, I think you have already done. I have already talked. We have the radiative transfer in X-rays and optical wavelengths. We can do for each phase of the system, so you can follow the variation along the Wydorf rotation. And of course, we calculate all the Stokes parameters because we are interested in polarimetry also, not only in photometry. So this is the geometry of our problem, is the exact geometry that you have in our code. Here is the equations that we solved to have the profiles of the temperature and density in the post-shock region. Here, the main ingredients are the magnetic field. The mass transfer is very important, and the size, because we have, okay. It's too complicated to talk about this now. Maybe what is important to say is that to have a complete description of a given data set, the main parameters of the problem is the inclination of the binary, because it's very important, the viewing angle by which we see the system, the Wydorf, the post-shock region. We need to have the size of this post-shock region, the real size in 3D dimension. We have to have the position of the post-shock region on the Wydorf surface, the magnetic field, of course, the direction of the magnetic field, because the magnetic field is not necessarily aligned with the Wydorf rotation, the mass accretion, and the Wydorf mass. Okay, so we can use as input for our code, if you try to get an idea of parameters of those systems, we can give the optical light curves and or the optical polarization curves and or the X-ray spectrum and or the X-ray light curve. So I will give you some examples and how they compare with some observations. So here is finally the optical polarimetry of a magnetic cataclysmic variable. In this case, we have a polar. So we see the circular polarization in a night varying between 0 and 30%. So very polarized object. We like very much to work with those objects because it's not so difficult to get good polarimetry. So in the top panels, we see the variation in flux. You can see also the magnitude of the object in R and I bands. And in the in the bottom panels, you see how the system vary from cycle to cycle. Here, by eye, you can have an idea of the orbital period, the white dwarf spin period of the objects. So this data was collected in our observatory in Brazil in a 1.6 meter telescope in a park in Elmar using the Azepol polarimeter developed by Antônio Mário Magalhães. So here is the same data now in 4 bands, and we have binned all data that we collect in many nights, and then we have the total flux, the circularly polarized flux, the linear polarized flux, and those lines, the blue and red lines above that you see in those figures are our models to those observations. And here we have the parameters that you obtain for this object. For instance, the white dwarf mass, the mass accretion rate, magnetic field of 2080 megagauss, and also the orbital inclination. On the top right, we see the profiles of density and temperature on the post-shock region. And in this small movie, the purple region is the post-shock region, and the green line is the magnetic field X, and the red line is the spinal cord of the magnetic accretion column. Is one magnetic field line that we use to build the model. Of course, we have many other magnetic field lines, but we show one to make the figure simple. Okay, here we have a very recent result. This object, I am bad in English, and with numbers I am really, really bad. V1082 Sagittarius. So this is a cataclysmic variable, and recently, just 1-2 weeks, we put this paper in Astrophysics. We measure a very small circular polarization by the way, also in a very small telescope. This result is from a 60 centimeter telescope. Here on the left, we see that the circular polarization of this object is about 1% or smaller. We got data on many nights, and we could see very clearly a period in the circular polarization. So with this result, we confirm, or we are sure that we are talking about a magnetic cataclysmic variable. In this case, the white dwarf spin is different from the orbital period. So we have an intermediate polar, not a polar. And this is the white band. So a preliminary modeling of this system is here in blue. The points are our data binned in the spin phase. And for this object, we estimate the magnetic field of around 11 megagauss. Okay, this is a work in progress, but I would like to show you those figures only because here we are fitting the flux in optical regime, the polarization in optical regime in 3 bands, I think it's V, R, and I, and also the X-ray spectrum. Okay, so we have a same model that gives. Why this is preliminary? Because we are getting some very strange parameters, and we need to see what's happening and if you are not doing something wrong. but we hope to have these results near in a paper. And all those data were obtained with the EASEPO polarimeter. And I would like to finish showing some results on this new instrument that is in our telescopes since 1-2 years now. This is a new generation of the EASEPO polarimeter, but it works in 4 bands simultaneously. Okay, so we have a camera. You can use it as a photometer or as a camera or as a polarimeter. And the very nice aspect of this instrument that we can have 4 bands simultaneously. And for variable objects, this is a very nice property of the instrument. Here is the observatory. The largest dome is where this telescope is installed. You can see that it's a very nice place, very green, not wonderful for astronomy, but okay, we have some good nights there. Here is the instrument in the telescope. And I will show you some preliminary results on some polars in this case. So I think those figures are not very good. But anyway, on top, we see simultaneous obtained data. So in blue, red, purple, and red, we see G, R, I, and Z is Sloan bands. Spark 4 works with Sloan bands. So if you, for this object, for instance, you see eclipses very well defined in blue, but not very well, not so present in red. So here, probably what we are seeing is the different wavelength dependence of the post-shock region emission, and maybe a segregation, a spatial segregation of the emission on this region. And below, we see the polarization, which is simultaneously obtained in all bands and also with photometry. Okay, all this data is some hours of telescope time. Okay, so of course we need to the idea here is to apply the Cyclops code to really understand what's happening. For instance, here we see differences from cycle to cycle, and when we don't have simultaneous data and you see difference from cycle to cycle, we always see. Let's put in a different way. In one night, you do one band. In the following night, you get data in another band, and you see differences. Those differences is because you are seeing a different band, or because the system really changes a little bit. When you have simultaneous data, you don't have this question. So this is a very important restriction or restriction to the model. And we are doing this in the next, in the future. This is another object. Here you have this is an object that you have also spectroscopy. Anyway, here you have I give you the idea of the magnitude of the system. And again, we have flux and polarization varying along the spin period. And this figure, I think it's very, very nice because the polarization curve. Why? Because the the angle in which you have the maximum of polarization depends on the wavelength. And here you see very, very clear that the peak of the peak here is the negative now, okay? So the higher polarization occurs in different spin phases, as we know that has to happen from cyclotron equations. And this figure really shows this very, very clear. So with this kind of data, it's a very nice chunk of data to have an idea of the magnetic field of those systems. Okay, so Evkaristo, and if you have any questions, I am very happy to answer them.
Great. Thank you very much, Claudia. We have a lot of questions, especially me, but some of them I'll touch base offline because we need to respect the time. But everybody, please feel free to raise your hands now and let's start it. I see Nick has his hand up, please.
Thank you very much for a very clear presentation of cataclysmic variables. Extremely clear. Thank you. I have some naive questions. In the not the last slide, not the very last, but the one before, where you said that this particular polar shows no eclipse in red colors. So what does that mean? Does that mean that the red emission happens high up so that it's not eclipsed, or and all the others are low below? You don't know yet. Okay.
We don't know yet exactly. You have to model this, but
Okay.
now having this kind of data, I think it should be very difficult to model that. But now we have data to understand this kind of spatial segregation. It is on longitudinal. It's not clear, for instance, because of the density. If you think about the trading region, you can have the trading of different densities in different portions of the equator. So you can have different densities going to different places on the white dwarf. So we have to see what we can do with models.
Okay. I understand the difficulty in modeling these systems, and not only these systems, just about every system. And so approximations are made in the modeling.
Yes.
Yes. In particular, the accretion column is taken to be cylindrical, right? In all the
No, it's not cylindrical. It's not cylindrical. No, it's curved. I have to. The shock solution is one-dimensional, and we have a lot of approximations there.
Right. It's the shock that I was mentioning.
Yes.
The shock happens near the neutron star, near the white dwarf.
Yes, but it's not cylindrical. It has some aperture to mimic the aperture of the magnetic field lines.
But still, if I cut this column, I get a circle, right?
Yes.
Yes, right. This is what I mean cylindrical.
Yeah. Yes.
It's axisymmetric. It's axisymmetric.
Yes.
On the other hand, simulations have shown, Romanova, for example, has shown that the accretion, the footprint and the cross section is not a circle. It's more like a crescent, like a new moon or something like that. So it's more difficult, but nevertheless, we should do the simple problem first and then go to more complicated.
But in the radiativity transfer, in the shock solution, you are correct. But in the radiativity transfer, we consider not a cylindrical shape.
Okay.
For instance, so here you can see that our footprint is not rounded, and
Okay.
even here, in fact, we have to have the solution of this object. You have to have this elongated region along the longitude.
Right. This is what I was saying before, that the crescent type.
Exactly.
Crescent.
Exactly.
Okay. I have more questions, but I will let other people ask, and then I will ask at the end.
Thank you so much.
Costa?
Yes, hi. Can you hear me?
Yes, perfectly.
Okay. Thank you for the nice talk. I have a quick question about the last plot that you showed with the polarization data. Yes, there. So I'm a bit confused. What is plotted on the y-axis? Is it like 50% polarization? And what's the negative sign?
Exactly.
So
it's
you have
50%. Oh, in fact, no, it's not, because in order to not superpose the data, I have included the offset. But let's see the blue points. The blue points do not have any offset. So the blue points, we see circular polarization from -10 to +10.
Okay, so the plus minus refers to a right hand and left hand, I suppose.
Exactly.
And
Exactly.
okay, now I understand. So the blue one actually touches -20. So you have 20% polarization.
Yes, exactly. Here. Yes.
Okay. Wow. Yeah, that's close to the upper limit, right, for synchrotron.
In fact, I think we have objects that are more polarized than this. I think the how to say the reference to polars are 70%. And also in this object, I think here, you see, we go to 30%.
So how do you explain these huge polarization fractions?
They came naturally from the cyclotron expressions. It's not a problem to have a polarization as high as this. I don't know. I don't think I have hundreds of backup slides. But if you go, for instance, to Vikramasinghe Maggot, a very old but a very important paper, 1982, you can see some models of punt form, very, very basic, but very important because they are basic models for synchrotron radiation. And you can have, it's not a problem to have a polarization degree as high as this. In fact, I think here you see a lot of information in this slide, but in order to correctly model, because let's start by the beginning. Here is polarization and flux. Here is flux, total flux and circularly polarized flux. Okay, here we are really talking about Stokes parameters in flux. So everything is in Jansk here. Okay, we can have some problem to calibrate, but we are talking about flux, even in flux and in polarization. And you see that the flux, it goes to the polarized flux goes near zero, but not completely at zero. To correctly have all these levels correctly model or to have these exact levels, we have to add unpolarized flux in all bands. You see, it is what I'm saying here is that we have the models have too much polarization. In fact, we have to add unpolarized flux in order to have the polarized flux that we really observed. Is it clear? I did a lot of confusion.
Yeah, I think it is. Thank you.
Joanna?
Yeah. So first of all, thank you for this very, very interesting and straightforward talk. Maybe my question is kind of basic, but still, I'm going to ask. How much can you tell about the life cycle, or in other words, the age at which you can see this cyclotron radiation in these low mass white dwarf binary systems? I mean, what kind do you expect to see any kind of difference in the optical polarization throughout the life of the system?
Yes, because I think I can answer you by two ways. First of all, the evolution of a cataclysmic variable. I'm not talking about the evolution of the binary system, but if you think only about the cataclysmic variable phase,
Exactly, yes.
you see an evolution from larger orbital periods to smaller orbital periods. Okay, and this should be happens or together with this, we should have a decrease of mass accretion. Okay, so for instance, the mass accretion rate that we see in this table, if we see for this object in 1 million years, this mass accretion should be different. And if the mass accretion is different, the top right solution will be different, because these profiles depends on the mass accretion rate, even if you have a same magnetic field. So if you could follow an object along its life as a cataclysmic variable, even if the magnetic field is the same, does not vary, what I think is the case, the emission should vary, because the mass accretion rate will vary. And this is one aspect. And another aspect is that we can use the population of cataclysmic variables to make a population synthesis and understand how is the evolution of those systems, and even how those quantities evolve along the cataclysmic variable phase. I don't know if I answered
Yeah.
question.
So you kind of expect to have the same pattern in optical polarization through the life of this system, which is going to be quite the same for the various different optical bands that you use in polarization? This diminish, you said, you mentioned, or do you have any idea about this? And the other thing is maybe, and after that, okay, so you can, based also on population synthesis models, can you determine maybe the age of the system?
I start by the last question.
Yes.
The orbital period is a kind of a proxy of the age of the system as a cataclysmic variable.
Okay.
More or less, okay, not
Okay,
perfect
yes,
because,
yeah.
but it's a kind of proxy. So if you have this object that you are seeing here is an object with a very small orbital period. So this is an old cataclysmic variable, probably, okay, because it is in the end. The orbital period is near the minimum orbital period. So it should be a very old object as a cataclysmic variable. The other question, how the polarization, if I understand correctly, how the polarization of a magnetic cataclysmic variable varies along its life as cataclysmic variable.
According to the different optical waveband. Or you don't see this kind of...
I would not add this qualification, this final qualification, because I think what we have is, as I quickly mentioned in the beginning of the talk, the presence or not of a disk is defined by the magnetic field, but also by the mass accretion rate. So a possibility is that we evolve. This is an open question, okay? But one possibility is that we evolve from an asynchronous magnetic cataclysmic variable with a disk to a synchronous magnetic cataclysmic variable without a disk. And in this case, we are going to have an increase of the polarization because the accretion disk is a source of unpolarized flux. So we are going to have a dilution of the polarized flux, so a decrease of the polarization. But for instance, if you think of a polar, I really don't, I cannot answer you on top of my heart.
Okay, yeah.
If you expect an important difference in polarization, maybe a little bit, because the profiles will be different. So we are going to have a different temperature and density profile that will impact the synchrotron radiation. But how large is the difference? I have no idea.
You cannot tell. Okay, yeah. Thank you. I'm more than covered. Thank you.
Any more questions? Nick, would you like to continue with the questions you left for the end, since I don't see any other hands raised, or should we let Claudia rest? No? No other questions? Okay. Okay, so thank you very much, Claudia. It was really a pleasure. And as you saw, everybody was really interested in polarization, obviously, and cataclysmic variables.